Hi, welcome to Astronomy Unlocked. My name is Phil Harrington. I'm a contributing editor for Astronomy Magazine, and today I'm going to talk a little bit about how to choose your best binocular for viewing the nighttime sky. Binoculars have been near and dear to my heart since I first became interested in astronomy way back when I was in sixth grade, and my science teacher assigned the class to look at a total lunar eclipse. Well, I had my binoculars with me, my family's binoculars with me at the time, and I took a look, and I was just mesmerized. Now the eclipse lasted what, 90 minutes, something like that, but something struck a chord in me which I still can't explain today. I was smitten with astronomy, and those binoculars were an integral part of that. And it's continued to grow and grow and grow. So I've found binoculars to be an excellent tool, not just for people with a passing interest in astronomy, but for those of us who are really bitten by the bug. And so I'd like to talk a little bit today about how to use binoculars to share the universe with your friends, your family, and others as well. Because again, excellent tool, wonderful tool for viewing the nighttime sky. However, in order to choose the right binoculars, it's good to understand some terms that are used when talking about binoculars in general, not just for astronomy, but for any purpose for that matter. So I'd like to go over a little bit about what I call Bino Babble, some terminology that you probably have heard, some of which you're probably familiar with, others maybe not, just to make sure that you understand the implications and how they all interrelate with each other when it comes to viewing the nighttime sky to the best advantage with binoculars. So I'll talk a little bit about magnification, aperture, exit pupil, prisms, coatings, field of view, eye relief, and also interpupillary distance. Okay, so let's dig into some of these terms. Beginning with numbers. All binoculars are specified with a pair of numbers. When we talk about how large a pair of binoculars is or how much they'll magnify and so forth, these two numbers are really key for understanding. The first number is the magnification. Okay? The second number is aperture. So, for instance, if you have a pair of 7 by 35 binoculars, I know it's written 7x35, but it's typically pronounced 7 by 35. Just like you go into a lumber yard, you want to buy a 2 by 4 piece of lumber. You don't want to buy a 2x4 piece of lumber. They wouldn't know what you're talking about. So, 7 by 35 binoculars, as an example. 7 power, make everything look 7 times larger than your eye alone would see it. And then 35. 35 is the diameter of the two front lenses, the objective lenses, as they're called, expressed in millimeters. So in this case, for 7 by 35 binoculars, 7 power, 35 millimeter objective lenses. Now, then you have 7 by 50 binoculars, 7 power, same magnification, but larger objective lenses, 50 millimeter or about 2 inches or so in diameter. Other numbers that you see on the screen over here are typical combinations. There seem to be sort of a standard set of magnification and aperture pairings, 10 by 50, 10 by 70, 16 by 70, and so on. Okay. The example you see, the photograph you see over here, a pair of 9 by 63 binoculars from Celestron. Again, another common combination of numbers, magnification and aperture that you see. It's important to know these numbers for a couple of different reasons, not the least of which is they affect directly the size or the diameter of the cone of light exiting the eyepieces, which is what you're looking through, and entering your eye's pupil. That exiting cone really is a cylinder of light coming out, is referred to as the exit pupil. Ideally, you want the exit pupil to roughly match the diameter of your eye's pupil. Well, of course, under dim light, you know your eye's pupil dilates or expands. In bright light, of course, it contracts down, gets smaller. Where if we're talking about viewing under night sky conditions, then your eye is going to be, if not fully dilated, more dilated than if you're in a bright room or outside during the day. And so, how do you determine the exit pupil of your particular binoculars? You simply take those two numbers, aperture, and divide it by magnification. Let's go back to my 7 by 35 binoculars. 35 millimeter aperture, okay, divided by magnification, which is 7. And so the exit pupil is 5 millimeters. Go back to the other example of 7 by 50 binoculars, 50 for the aperture divided by magnification. So 50 divided by 7 is about 7, 7.1, something like that. It's important to know that combination because not all combinations work for everybody under all conditions. I'll talk about that in a little more detail in a little bit. Something else to take into consideration, the prisms. Inside every modern pair of binoculars, you have a set of prisms inside, match prisms. The function of those is to take the image entering through the objective lens and bounce it around so that when it finally exits through the eyepiece and into your eye, everything is right side up. Now, admittedly, for astronomy, up and down, left and right really doesn't have a lot of bearing. Everything is up, and down is toward our feet, toward the center of the earth. And so up is up, always. But when we talk about orientation, we think more in terrestrial terms. Certainly, a pair of binoculars, you don't want to use binoculars to view a ball game and all of a sudden have the players upside down. And so everything has to appear right side up. And that's the function of these prisms. Binoculars use two different types of prisms depending on the model and the design of the model. We have roof prism binoculars, and we have Porro prism binoculars. Roof prism binoculars, very thin, very sleek barrels, very common, very popular with bird watchers, especially because they're lighter, more compact. And you can see just a cutaway view through them on the left-hand side of the screen, versus Porro prism binoculars on the right, which is the more common design. If you ever see just a stereotypical image of a binocular, it's going to be Porro prism with the familiar zigzag barrels. Inside, again, you have two sets of prisms. The function there is to, during that zigzagging back and forth, to make sure the image coming out of the eyepiece is right side up. A little closer view to Porro prisms. That's what they look like if you get a little more detail. The objective lens is labeled over there. You see the sets of prisms. And the red line, that's the light path, bouncing off different surfaces in the two prisms and now through the eyepiece. Those are Porro prism binoculars. Again, the more common design. Versus roof prism binoculars, it's a sleeker barrel, a little bit easier to carry, a little lighter weight. Again, common for bird watching, certainly. You can see there the prisms are nested on top of each other in such a way that the light bounces all over the place. You see there are 5 contact points in the prism, so it exits out through the eyepiece. That's referred to as the Schmidt-Peckham design. Another design of roof prism binoculars called Abbe-Koenig. You can see the light bounces through, hits 3 surfaces in the prisms set before it bounces out through the eyepiece. Coatings. Coatings are also important. All binoculars nowadays, at least all binoculars that are well made, have coated optics. The idea of coatings to optics, you want to minimize or completely eliminate flare, such as you see in this picture over here. Here I'm looking at the moon, but you can see the moon is overexposed, but take a look at that little green moon over on the side over there. That's a reflection off the optics of the binocular. You don't want to see that. You don't want to see a ghost moon in your images, in your views. And so you want to look for coatings. And the manufacturer of the binoculars, such as Celestron here, will state typically on the tailstock or the back end of the binocular housing itself, the coatings. In this case, fully multi-coated optics. Those are great. That's really what you're looking for. But it gives you some other information on the tailstock as well. But what are we talking about coatings? Manufacturers use a single layer of chemical compounds across at least one lens surface. That's referred to as coated optics. Okay, at least one lens surface has a single layer of coating, a magnesium fluoride typically. Fully coated means that there's a single layer on all air-to-glass surfaces. You can tell immediately if you have coated or fully coated optics by looking at the color of the reflected light in the objective lens. Hold the binocular at sort of arm's length, tilted at an angle toward a bright surface, maybe a ceiling, for instance, would work. And you'll see color reflected in the glass, in the objective lens itself. It appears kind of purplish, like you see in the picture here. That tells you it's a single layer of optical coating. Binoculars that claim to be multi-coated, the color changes to sort of a greenish, kind of a strange greenish purplish combination, as you can see in the next picture that just popped up. Multiple layers, using multiple layers instead of a single layer, improves light transmission, also improves contrast. Okay, so multi-coated, or better still, fully multi-coated on all air-to-glass surfaces, they're about the best. I want to just give a brief note of caution. if you pick up a pair of binoculars and they say they have ruby coatings or green coatings, those don't really work well. They look really pretty in colors, they look really pretty in ads, but in reality, those coatings really don't serve any positive purpose. In fact, some would argue that they're actually a detriment. So you want to avoid those binoculars. Coated or fully coated are great. Multi-coated, or better still, fully multi-coated, are really what you're looking for. Now, admittedly, my first binocular from back when I was 12 years old had no coatings on the lens at all. Back then, that was fairly common practice, I guess, in some circles. I had no coatings at all. And so that actually, although it still caught my interest in astronomy, certainly, but that didn't produce the image that some of my later binoculars do produce rather. If you're looking at roof prisms, you want to look especially for phase correction coating. The problem with the roof prism design, light becomes partially polarized as it passes through the optical system, which results in two slightly out of phase beams of light coming along. If you don't have phase correction coatings to rectify that, you'll see images that have lower contrast and less resolution. The coatings themselves force the split light beam back into phase, and so the results are superior. So again, that's only for roof prisms, but phase correction coatings um, is really the better choice. In addition to the type of coatings, the manufacturer will also often quote field of view. Okay, field of view. In this example here, it says field of view 5.3 degrees. That means these binoculars will take in a swath of sky 5.3 degrees across. Okay. Nice wide field of view. Some manufacturers, though, prefer to express the size of the field as so many feet per 1,000 yards, okay, such as these over here, 378 feet at 1,000 yards. Well, what does that mean? That means that for these binoculars, if you had a ruler 378 feet long, if you viewed it from 1,000 yards or 3,000 feet away, okay, that the ends of that ruler would just fit into the field of view. Well, for astronomy, we're not looking for rulers. We're looking for how wide a piece of sky will fit into my binocular field. And so you simply take, if your binocular has that expression, take the number in feet and divide it by 52.5. And that'll give you the equivalent field of view in degrees. So for instance, in this case, 378 divided by 52.5 will yield a 7.2 degree field of view. Another thing to take into account is eye relief. Eye relief is the distance that you must keep your eye away from the eyepiece to see the entire field of view. Again, the manufacturer will tell you what that number is. It may not be on the binocular itself, but it will be with the literature and the specification sheet that is available for that particular pair of binoculars. If the eye relief value is small, you have to get right on top of the eyepiece to actually take the whole field of view in. If it's too large, then you have to hold those binoculars in front of you, making them difficult to support steadily. And so that's a concern as well. You don't want it too hot or too cold. You want it just right. Not too far, not too short. Here are some numbers that you're going to see. Very good, in my humble opinion, very good binoculars have an eye relief anywhere from 18 to 22 millimeters. Good is 15 to 18. As you get into the fair and the poor categories here, that gets close. Okay, again, these expressed in millimeters. They're 25.4 millimeters to an inch. And so for fair, you're looking at roughly half an inch or less in some cases. That's a real concern, especially if you have to wear glasses. Okay, now my glasses, I need them only for distance vision. And so I always take my glasses off when viewing through binoculars. But if you have astigmatism, like my daughter does, then you'd have to have the binoculars on when viewing through the eyepieces. Okay. In that case, especially, you want to have anywhere from, 15 is okay, but I would tell you with glasses, 18 to 22 would be the better choice. If you don't need glasses, then 15 millimeters would be perfectly fine. Less than 15 millimeters, I'd probably tell you to look at another pair. Okay. Interpupillary distance. What's yours? Interpupillary distance is the distance between your eye's two pupils. In other words, how widely separated are your eyes. There's a way to test that. you want to get a ruler expressed typically in millimeter units. Right? You want to take that ruler, you want to stand in front of a mirror, bathroom mirror is perfectly fine, and close your left eye. Hold the ruler in front of you so that the end mark of the ruler is exactly coincident with your right eye. Okay? And then, without moving, open your left eye and take a look at the exact millimeter mark that falls on your left pupil. That's your interpupillary distance. Manufacturers will express a range because binoculars with the central hinge can be adjusted, okay, to match your interpupillary distance. You want to see that they will. Some binoculars may not open wide enough. Some binoculars may not close tightly enough to take in your specific values. And so if you know what you are going in, then you can tell right away if the binocular will be useful for you. Because if you can't, again, line up the eyepieces with your eye's pupils, they're not going to work for you. And you have to look for another pair that will. Binoculars use two different types of focusing: center focus, as you see here, or individual focus. In the case of center focus, you have a central ring that you can turn with one finger, and both eyepieces will focus simultaneously. Individual focus, each eyepiece focuses separately from one another. In general, but not always the case, but in general, if you're going to be holding your binoculars by hand, as most people do, center focus is going to be easier for you to adjust. If you're putting binoculars on a tripod or some other support, then individual focus is great. Keep in mind that both of your eyes do not focus exactly the same. And so even with center focus binoculars, you can adjust one of the eyepieces individually. So you focus for the one eye using the center focus, then the other eye that maybe not quite in focus, then you focus that separately, and you'll get a sharp view in both eyes. You want to keep all this in mind as you go shopping for binoculars, because you want to go in, as I say, an educated consumer. You want to go in as an educated consumer when you're judging a binocular. Is it good for your needs? Is it good for your location? And so forth. Some people feel that bigger is better, and that's not true. Okay, that's not true. You're going to find that the bigger binoculars, yes, larger objective lenses, they take in more, not more sky, but they will brighten what you're seeing. Fainter objects look brighter. But how are you going to support them? If you're going to, like my daughter is showing here, if you're using a large pair of binoculars, you're going to find that holding something like this, and these are 16 by 70 binoculars, difficult to do. I mean, she's holding them correctly with her hands out by the objective lens. Most people grab around the prism, and they tend to wobble that way. But if you hold around the objective lenses, your cheekbones act as the other support. You can hold them steadily for a time, but they get really heavy really quickly. In general, when I hear from readers and others asking questions, I say you probably want to go no more than 10 power maximum and 50 millimeter maximum if you're going to be holding it by hand. Yes, some people say, well, I can hold 16 power binoculars, but for how long? See, that's the thing. For how long? Maybe you can hold them for a minute, but after a while, they're going to get heavy, and fatigue is going to set in, and it's going to be very difficult to hold them steadily for any period. Another myth. People often will say that 7 by 50 binoculars are the best binoculars for viewing the nighttime sky. They're so-called night glasses. I'm not sure where that began. I believe the idea, because it's not true, the idea I think originated during World War II, when the Navy was commissioning various companies to create binoculars for night use on ships. And they contracted out 7 by 50 binoculars. Well, it turns out 7 by 50 binoculars are not necessarily the best. Okay? It depends on you, depends on your location. I said before, ideally, you want the exit pupil to to be no greater than the entrance pupil of your eye. Well, here's an illustration of what I'm talking about. On the left-hand side, under dark sky conditions, your eye comes pretty close to fully dilated. Okay? With young eyes, your pupil may dilate to roughly 7 millimeters, roughly. Okay? But that's if you have young eyes and under dark sky conditions. Even with the same young eyes, under light polluted conditions, your eye's pupil may not dilate to more than 5 millimeters. Okay? And so, with those 7 by 50 binoculars with a 7 millimeter exit pupil, your eye's not taking advantage of all the light that the binocular is transmitting. But at the same time, the larger aperture will also transmit more light pollution, sky glow, and it will make the image appear more milky. So, in that condition where you have a limited pupil to maybe 5 millimeter, your eye's pupil that is, then maybe 7 by 35 binoculars or 10 by 50 binoculars would be a better choice because each delivers a 5 millimeter exit pupil, again, matching you and matching the conditions. It's also a sad fact that as you get older, your eye's pupil does not expand or dilate as fully as it used to. This chart, which comes from a vision research publication back in November 1999, but it's still accurate today, shows you that you're at your best before the age of 20. And after that, it's a slippery slope down. So my eye right now, even under ideal conditions, may dilate to 5 millimeters, and that's all. Okay? As we age, you'll see it slopes down. It about evens out when you get toward about 80 or thereabouts, so between 70 and 80. But your eye is going to not be able to do what it used to do, even under the same perfectly dark conditions. So again, purchase a binocular to match both your conditions, your sky conditions, but also you in terms of age. If you're looking for Porro prisms, make sure that the prisms are made of BAK4 glass. Less expensive, we'll use BK7. BAK4 have a higher, what's referred to as index of refraction. To put it in somewhat layman terms, more light get transmitted. Okay, with BAK4 than BK7. BK7 must have a surface aluminized to reflect light through, whereas BAK4 do not. So again, looking for binoculars, Porro prism specifically, BAK4 would be your better choice. And again, the manufacturer will say it on the tailstock of the binocular. And just a reminder again, the cutaway view, the Porro prisms, that's what's made out of the BAK4 glass. How do you know if your binoculars have BAK4 or BK7 prisms? Well, if the manufacturer doesn't tell you, it's easy enough to tell yourself. Take the binoculars, again, aimed at a bright lit ceiling is a great idea, or maybe the sky, as long as you're away from the sun. Hold them at arm's length, and then look at the eyepieces. Okay, at the eyepieces from a distance. If you see what you're seeing on the right-hand side of the slide over here, BAK4, it's a evenly illuminated full circle, whereas BK7 on the left, you notice that little diamond shape? That indicates light fall off due to lower index of refraction. And so again, the image won't be quite as bright or quite as sharp. Now, my original binoculars had BK7, and they were great. Okay? They were great. BAK4 will produce a somewhat superior image, but BK7, if you have a BK7 binoculars, I'm telling you to get rid of it. Use them to their fullest potential. But if you're purchasing binoculars, then BAK4, as long as your budget permits, would be a better choice. Things to look at also, optical flaws. Okay, so optical flaws. Field of view. Sometimes less is more. In other words, instead of using wide-angle eyepieces and wide-angle binoculars, have somewhat narrower field of view. Here's an example with astigmatism. I'm looking at the Pleiades here, the Seven Sisters. You notice how the stars in this illustration on the edges are out of focus pretty dramatically, whereas those in the middle are in focus. That's due to astigmatism. Not your eyes astigmatism, the binocular astigmatism. Things to look for when judging if a binocular is suitable for astronomical viewing, because you want sharp points of stars all across the field of view. At the same time, distortion. Put the moon toward the edge of the field. Is it round like this, or does it appear rather oval? That's distortion because of the optical system of the binocular. Another example, field curvature. The stars are sharp in the middle, but toward the outer edges, they're not distorted, but they just aren't focused. They look like little balls. Then when you go to change the focus, the stars at the edges come into focus, but then the stars in the middle are out of focus. That's due to field curvature. Another optical imperfection you may notice is referred to as lateral color. You'll notice in this illustration how there's sort of a glow or a color around some of the stars, kind of a purplish, see more toward the edges than the center. That's referred to as lateral color. You can also check for various aberrations outside during the day. Field curvature, it's sharp in the middle, but the outside, it's soft in focus, but also has sort of a curved look to it. You can check for barrel distortion looking at a brick wall. Are the bricks perfectly horizontal and vertically aligned? Or if you take a look at my reference lines here, notice at the top and the bottom how the bricks are not, even though they are perfectly straight, they're not in this view because of curvature. Okay, it's referred to again as barrel distortion. Looking at trees, you can see colorful edges, sort of purplish on one side, greenish on the other, due to chromatic aberration. That tells you the optics aren't as sharp as they could possibly be. So things like that you're looking for. If you purchase binoculars that have ED or extra low dispersion lenses, then a lot of those images that we just saw won't apply to you because they're the best of the best ED glasses, and they will correct for all those imperfections. How are you going to hold your binoculars? Something else that a lot of people don't consider. Binoculars typically, like many of them do, have tripod anchors built into them. Okay, you have to have an adapter of some sort, typically they're these L brackets, that will allow you to attach the binocular onto a camera tripod. Problem is, most camera tripods are designed to have the camera aim more or less horizontally, not vertically like we want our binoculars for looking at the nighttime sky. And so you might find yourself looking at the nighttime sky like I'm doing here, or maybe like I'm doing there. You need to have a tall tripod. Keep that in mind, especially if you're looking for larger binoculars, larger than 50 millimeters, up to 70 millimeters, 80 millimeters in aperture. They're pretty heavy. You need a decent tripod to support them on. You could always purchase, these are fancy, these flexible parallelogram mounts. They're wonderful. Some industrious astronomers, amateur astronomers actually make their own. Others purchase them. They're very, very good. Speaking of industrious astronomers, how do you like these binocular mounts? I love these things. You have lawn furniture on Lazy Susans. The Star Rocker over on the right-hand side, that was a commercial. Was that commercial? I think that was actually homemade as well. But great designs for the advanced binocular astronomer. Well, that's pretty much all I have to offer here. I would love to hear any questions or comments you might have. You can certainly contact me through my website, philharrington.net, and I'd be happy to answer any questions that you might have. Okay. Till then, remember that two eyes are better than one. Thank you.